Hi everyone, in this video we are going to be taking a look at numbers that are too big for us to comprehend. Now let's get into the video. We'll start with the number 1. Now 10, 100, 1,000, 10,000, 100,000, a million, a billion and a trillion. Now let's take a deep look at the last three numbers, a million, a billion and a trillion. Although they all sound similar, they have a massive difference in value. Let's take for instance, a million minutes is only around 2 years ago, but a billion minutes was around when the First World War started 108 years ago. However, a trillion minutes ago was when the first humans ever emerged on Earth, which was around 2 million years ago. We could go on like this forever, but this is not the easiest way to get to the big numbers. Instead, we have to use operations. The most basic arithmetic operation is addition, which is when you combine two values together to get a greater value. Example, 3 plus 3 equals 6. The next step about this is multiplication, which is when the digit a is added to itself b times. Example, 3 times 3 equals 9. The next is exponentiation, which is repeated multiplication and also known as index notation. 3 to the power of 3 is 27. The next on the list is tetration, which is repeated exponentiation. 3 tetrated to 3 is the same as 3 to the power of 27, which equals 7.6 trillion. However, if you change the digit on the top left corner from a 3 to a 4, you get 3 tetrated to 4, which is the same as 3 to the power of 7.6 trillion, which is a number that is 3 trillion digits long. Penultimately, we have penetration, which is repeated tetration, and in written form is shown as 3 arrows in the middle of the two digits. 3 penetrated to itself is the same as 3 tetrated to 4, which, as we said earlier, is a digit that is 3 trillion digits long. Lastly, we have hexation, which is repeated penetration, and is also shown as 4 arrows in the middle of the two values. 3 hexated to itself is a way to get us to the Graham's number, which is one of the biggest numbers. Let's assume that 3 hexated to itself equals G0, which means G1 would equal 3, then G0 arrows. Just like G1, we could have G2 with G1 arrows in the middle, and then we can have G3, G4 and so on, until G63, which is the Graham's number. The Graham's number was first used by Ronald Graham in 1980 and was also rewarded the title of being the largest positive integer to ever have been used in a published mathematical proof, and also earned the Guinness World Record for it. But we have come a far way long from 1982 and the Graham's number, and the new way to get to the largest integer is the tree of 3. To understand the tree of 3, we need to play a game called the Game of Trees, using colourful seeds. There are only 2 rules for this game. Rule 1. The nth tree cannot have more than n seeds. Likewise, the first tree cannot have more than 1 coloured seed, and the second can't have more than 2 colours, and the third, likewise, can only have 3 colours. The second rule of this game is that no tree can contain itself twice, which is proven by the first and the second tree on the screen right now. The first and the second tree cannot be joined due to the fact that the first tree contains a part of the second one. The way to write this is the tree of n. The n represents the number of seeds you are allowed to build the tree, and the value of the tree of n is the number of trees you can produce using only n seeds. The tree of 1 has a value of 1 due to the fact that you can't use the same tree twice. Then we have the tree of 2, and using only 2 coloured seeds we can make a total of 3 trees. However, Using the combinations of only 3 colored seeds, we can make so many trees that no one on Earth have been able to figure out the number of trees we can make using the tree of 3. And that is the value of the tree of 3. Now let's take a look back at the Graham's number. We don't have to stop at G63. Why not go to G64 or even G100 or G1000 or even G1 million? However, all of these combined are still minuscule compared to the tree of 3. Just like the Graham's number, we can keep going with the trees. Why not take a look at the tree of 4 or even the tree of the Graham's number or G63 or even the tree of 3. And why not even the tree of G63 or the Graham's number? And with this, thanks for watching this video. See you again in the next video. Bye!